So let's continue to discover steady state electric current. I want to formulate Kirchhoff's current law, right? So let's reinvestigate or revisit the definition of current. Well, current is generated when you have charge movements over a certain time. But now I'm adding a negative sign, and I'm using partial differentiations to reflect the fact once you have charge flowing, then basically the number of charges is reduced. Okay? So this negative sign is taken into consideration if you have charge moving out, then inside the box you have fewer charges, right? So another way to understand current is the rate of change of charges in certain constant value, okay? If the number of charges is reducing, then you have produced current. But now that we know charge, the number of charge is the volume integration of the charge density, right? This is by definition. But we also know that the current is defined as the current density making a surface integration, right? Current density by definition is current per unit area. So this equality is straightforward, and this equality is straightforward. And this is where divergence theorem is very important. We have the vector current density making a closed surface integration that can be transformed into the volume integration of the divergence of J over the volume, right? This is basically divergence theorem. I'm free to convert between volume integration of the divergence of the vector field and the surface integration of the vector field itself. Now, by comparing the terms, I have the volume integration, I also have the volume integration, which means the integrands must be equal. So this is telling you divergence of J is equal to the negative change of the charge density. I mean, try to formulate or try to come up with a sentence that you can understand yourselves when looking at this equation. This is telling you if you have the change of the charge density as a function of time, then you would have some flowing of the current densities, right? This change is in time, but this change is in space. Divergence is a net outward flux of your vector field in certain space, okay? So this is a generalized equation, but now we are concerned only about the steady current. So what does it mean to have a steady current? Under steady current assumption, this rate of change of the charge density has to be 0, right? Since the charge density cannot change as a function of time, we have steady state. And therefore, divergence of J has to be 0 under this assumption. So what does it mean? Let's take a look at the blackboard. I have three different circuit elements connected together, forming a node, right? This point is shared by all these three elements. If I want to invoke divergence of J equals to 0, well, divergence means the net outward flux of the field. I can form a volume, right? A solid sphere centered at this node. And I evaluate the outward flux of J. And this is telling me the divergence, the net outward flux of the current density has to be 0 for this node. Okay? So it means this J2, J1, J3, right? They add up to 0. So I'm hoping you might be very moved or motivated because this is something you were forced to accept as Kirchhoff's current law. Kirchhoff's current law tells you for a given node, the total sum of the current has to go to 0. Or another way to understand it, for a given node, the total current coming in is equal to the total current coming out. So up to now, we have proved Kirchhoff's current law. This is coming from the assumption of steady state circuitry. So your divergence of J must be 0 because the rate of change of your charge density has to be 0 under steady state. Right? Now, I want to use this more generalized equation to show you about perfect metals. If you still remember, we talked about if we have a piece of perfect metal and we forcefully inject charges into it, over a very short time, all these charges would surface, right? So that the condition of no charge inside the perfect metal can be satisfied. So now we have the tool and we have the knowledge to prove it, right? Again, we start from this continuity equation. This is something we derived, right? Divergence of J is equal to the negative rate of change in my charge density. And that is called the continuity equation. But J equals to sigma E, right? This is something we also learned. J equals sigma E is the electromagnetic version of Kirchhoff's voltage law, right? So we combine this knowledge, J equals sigma E, but because sigma can be viewed as a constant, so it does not participate in divergence. All right? I have assumed I have a homogeneous piece of metal. So sigma is viewed as a constant. But then divergence of E is equal to rho divided by epsilon. So rho on the right and rho on the left. So this equation contains a lot of knowledge. This is like a basic summary to what you have learned up to now. This is something we learned as continuity equation, and this is Kirchhoff's voltage law in EM language, and this is using Gauss's law. The combination of three different knowledges, or knowledge. You cannot count knowledge. Okay? Simple equation contains a lot of knowledge. So this is a very simplified equation. All we have to solve is we move this right to the right. So we are interested in the rate of change of the charge density, right? We inject the charges into the metal. We want to see how it decays, how the charge density is decayed to 0, because inside the metal, ideally, we cannot have charges, and therefore the charge density has to be reduced to 0 over a certain period of time. This simple differential equation can be solved directly. I believe you are all capable of doing it. So basically, the charge density as a function of time is your initial charge value, and then you have exponential decay, right? Exponential decay, and that tau is called the time constant. And that time constant is, in this case, is epsilon divided by sigma. Tau is epsilon divided by sigma. So if you go back and check in your textbook for a certain ideal metal, you will find the epsilon value and sigma value, right? You divide them, you find the time constant. And that time constant typically gives you an extremely short duration, 10 to the negative 19th second. Super, super fast. So this corroborates what I showed you previously, right? If you have a good piece of metal, you inject charges into it, within such a short time period, all the charges will be forced to swim to the surface and stay on the surface. And therefore, inside the metal, you still have equal potential and you have no charge density. Okay? So try to appreciate these three equations, cascaded together, but combining a lot of the three different equations, laws, into a simple single equation. Right? Okay, so now let's investigate into boundary conditions. Why do we care about boundary conditions? Well, in reality, you might have different layers, different materials connected together. So if you only know the field or the current value in one medium, through boundary condition, we know the field and current values in all other medium. Okay? So let's revisit what we have covered up to now. Current density, J, is a vector. Under the steady state condition, divergence of J has to be 0. This is under steady state. So this is expressed in the differential form, but in integral form, we have a closed surface integration of J has to be 0. This is Kirchhoff's current law. On the other hand, curl of E remains to be 0, right? E fields are conserved. So J equals sigma E. So we have the curl of J divided by sigma has to be 0. Expressed in the integral form, in a closed loop integration of J divided by sigma has to be 0. So looking at these four equations and ask yourselves, whenever we think of boundary, we have two different materials, right? We have medium 1, medium 2. Whenever we have two different materials, we form an interface. So the boundary conditions are no more than, well, if we know the field or current in one medium with its magnitude and angle, we want to know what is happening in the second medium. You need to have this capability now. Divergence condition or divergence equation always tell you how the normal components across the two interfaces are related. Curl condition always tell you how the tangential components are related across the interface. Okay? So the tangential component, due to curl of J divided by sigma equals to 0, so the tangential part has to be the same. So therefore, the tangential part in the first medium of the current density divided by the first medium's conductivity has to be equal to J2T divided by sigma 2. Curl relation always tell you how the tangential parts are related, okay? Because you have to form a closed loop. The normal component is always taken care of by the divergence formulation. So J1n is equal to J2n. Okay? So we take a look at one example. We have two conductors. The top one is having sigma 1. The bottom one is having sigma 2. If I know I injected certain current density from the first medium into the second medium. So basically J1, the magnitude of J1 and the angle with respect to the surface normal is known. So alpha 1 is known, J1 magnitude is known. Can I deduce the magnitude and angle in the second medium? And that's the benefit of using boundary conditions. First one, tangential part of the E field remains the same, which means J1 times sine alpha means J1t divided by sigma 1 has to be equal to J2t, right? This one, J2t divided by sigma 2. Okay? Now, this first equation is telling you nothing more than curl of E equals to 0. Okay. But I want to train you in a different way. Look at the figure and take a guess. Which material is having a larger conductivity? Can you know it just by looking at the figure? Currently, J1t is shorter, right? J1t is shorter than J2t. So what does that tell you? It tells you sigma 2 has to be greater than sigma 1, right? Because J2t, a longer J2t has to be divided by a larger sigma 2 in order to be equal to a shorter J1t divided by a smaller sigma 1. Okay? So for you, you have to understand it. If a material is having a larger conductivity, it can produce a larger tangential component in its current density, and thus making the angle larger. Okay? So this is a training for you. If sigma goes up, alpha goes up, JT goes up. Okay? This is some capability that I want you to have. Try to summarize your own knowledge using your own word after a vast amount of part points and derivations. And then you carry it for the rest of your life. Okay, I know it's very difficult, but that's my anticipation. Okay, so we took care of the tangential part And now J1n is equal to J2n. So that's a cosine part. Okay. Again, like the dielectrics, we divide the two equations, we find the angle. Remember, alpha 1 is given. So now alpha 2 can be deduced directly. Now that we know the angle, we can find out J2 amplitude, right? J2 amplitude is just the summation of the normal component and the tangential component squared, and then we take the square root, okay? So this is basically mathematics. The key issue is, are you able to understand from these two basic equations, divergence of J equals to 0 under steady state current condition? And then you know, oh, this is actually telling me if I have an interface formed by two different materials, then the normal component must be continuous. And this curl equation tells me how tangential components must be related. Okay? By now, you must have this capability. Curl equations always tells you the tangential components. Divergence always gives you the normal components, how they are related. Okay? So if we have two conductors, things are quite easy, straightforward. What happens if, well, this is a very unique case. Again, we have two materials forming an interface. Okay? But what happens if, in this case, these are conducting dielectrics? What does that mean? Conducting dielectrics. Ideally, dielectrics are non-conducting, right? So these are bad dielectrics. These are dielectrics that actually permit to have some kind of flow of charge, okay, in the form of conduction current, right? So for these materials, we need to use epsilon and sigma to describe it. So usually, I mean, for pure conductors, we only want to have sigma. But here, they're imperfect dielectrics or imperfect conductors. We need to use both epsilon and sigma to describe it, right? So the first material, epsilon 1, sigma 1. Second material, epsilon 2, sigma 2. Now, let's try to investigate into this unique case. All right, so we want to understand about the current density, and we want to understand about the flux density. Now, remember, well, examination 2 is coming up. So whenever we talk about flux density across two different materials, usually divergence of D is equal to rho free. So remember, there might be charge densities deposited along the interface. If you don't draw this surface charge density, then you're not looking at the picture right. Okay? So this is a particular case where you have current flowing across the interface, but at the same time, you might have charges being deposited over the interface. Okay? So let's try to unveil the secret. In this case, if I have the tangential part of the current density, they must be equal. Each has to be divided by its corresponding conductivity. This is just the same. as our previous boundary condition, right? And this is also telling you tangential component of the E field intensity across the two materials must be equal. Normal component, nothing more. J1n equals J2n, right? Nothing more. But what is new here is for this imperfect dielectrics, D1n minus D2n equals rho s. This is something we covered, right? So in the normal direction, we have to take account into two facts. Even though you have a steady and equal amount of current density, you actually might have accumulation of charges on the interface. So this one, J equals to sigma E. So the normal component in the current density are equal can be reformulated into sigma 1 E1 normal component is equal to sigma 2 E2 normal component, right? And D equals to epsilon E. So D1n is now reformulated as epsilon 1 times E1n and minus D2n is equal to rho s. So as you can see, in the tangential direction, there's no story about the tangential component. But the normal component, it's quite exciting and quite complicated, right? We have two equations which needs to be solved simultaneously. The first one is telling me the current density. The second one is telling me surface charge density. So I can actually use the first equation to relate E1n and E2n, right? And then replace into the E1n or E2n in the second equation, and that's what I did. So basically, I want to know how to quantify the surface charge density at the interface, right? I can formulate rho s in two ways, right? Represented by E1 normal or E2 normal, it doesn't matter. What I do care about is looking at this result, or let's move on. I reformulated this rho s for you. So across the interface, you always have the normal E field intensity, right? Well, either you describe rho s in the form of E1n or E2n, does not matter, but look at these two within the parentheses. E1n is non-zero. Rho s is something we want to investigate, but epsilon 1 minus epsilon 2 and multiplied by sigma 1 divided by sigma 2. So my first question to you is, if you have two imperfect dielectrics that both can have conduction currents, when do we anticipate to have no surface charge density? Well, rho s to be 0 can be satisfied both by these conditions equal to 0, right? So which means epsilon 1 is equal to this amount, or this amount equals to that, the same, right? So think about it. When can there be no surface charge density? Rho s can be 0 only if this one goes to 0, right? When this one goes to 0, you actually have a very particular ratio of the material conductivity to the permittivity. So for both material, you have to have the ratio of conductivity 1 to permittivity 1 equaling conductivity of material 2 to permittivity of material 2. Now think about it. I mean, what are the chances for you to have this happening? And magically, you just chose 2 materials and they obey this relationship. It's almost impossible, right? I mean, gold and silver, I mean, you expect this relationship to hold? Probably not, okay? So as a summary, whenever you have imperfect or leaky dielectrics, so the dielectrics, they actually do carry current, you always expect to see resulting surface charge density. The magical case is this ratios hold. Then you have no surface charge density. But that's too rare. It's almost impossible. But the second possibility is when both materials are non-conductive, right? Think about it. Initially, we assumed these 2 are imperfect dielectrics, so you're allowed to have conduction currents. Because of conduction current, and even though sigma 1 does not equal to sigma 2, but divergence of J equals to 0, it forces you to have a constant and continuous flow of current in a normal direction. In order to meet that, some remaining charges from this one must be held as a prisoner at the interface. It cannot flow across, right? And therefore, you have surface charge density. It's due to the mismatch between sigma 1 and sigma 2. But now everything will be relaxed if the 2 materials are perfect dielectrics. Perfect dielectrics, you don't have sigma 1, you don't have sigma 2, and you don't have J. So in that case, you don't have the surface charge density. So in the case where both sigma 1 and sigma 2 are 0, you have perfect insulators, non-conductive, you don't have surface charge density. Okay? So we can actually learn a lot from the understanding of boundary conditions, right?